like to share a few thoughts on some basic principles that we follow when we develop a network of weather stations. Um, let's start saying a few words about the hexagons that we use in order to divide the Earth. We use the hexagons that you've already seen on our Explorer. The size of the hexagons was originally chosen to fit the size that the helium network used. However, covering an area of 5 square kilometers and having a maximum diameter of 2.8 kilometers, these cells are actually ideal for facilitating the scientific purposes of the project. So according to various studies and the World Meteorological Organization, the smallest scale phenomenon that a typical weather station can detect and measure is a convective phenomenon, like a shower or a thunderstorm. The typical minimum diameter of such a shower may be 1 to 3 kilometers. So actually, at least in a flat area, we have a station. We could have a station every 3 kilometers. We could be able to capture all these phenomena and measure the precipitation effectively. However, in most cases, we need more than one stations in each of these cells for a variety of reasons. And of course, we will discuss all these reasons in the next slides. Certainly, distributing weather stations in a large area is a really complex problem, although there are several scientific studies proposing approaches for designing a weather network. Most of them use an initially developed network, and then they find the ideal locations and number of weather stations to represent the weather conditions sufficiently. Of course, different cases require different densities of weather stations. As an example, we need different spatial densities for monitoring the earth flow within wind farms, or for identifying damage by a hailstorm, for example, for insurance market purposes. So in our project, we need to find a different method as we build from scratch a new network of weather stations. So we built a model, and we found that having a limitless number of stations, we should place stations every 2.5 square kilometers to 136 square kilometers. But this is the ideal scenario, that we have limitless stations, and we also aim to support even the most pretentious cases. But this is not helpful at all in our case when we start from scratch and we have a limited number of stations. So covering underserved areas needs a different approach. And here are the three main rules we need to follow. The first one is distribute the weather stations as uniformly as possible in order to, to show that we have a coverage over an area. Then we need to cover areas with different characteristics regarding topography and land use. We will expand on this in a bit. And of course, if it's possible, avoid areas that other networks have already deployed stations. I know that this is difficult for many reasons, but let's try to avoid too many stations, or to deploy too many stations where other networks have large densities. Note that we need stations even there. Of course, we need stations there, but avoid spending a large number of stations in areas that other networks serve. Here, there is also an active link of a website that's a synoptic data. This is actually a company, and this site hosts several world networks, and so you can use it to find which areas to prefer less than others, let's say. I can share. Yeah, of course.
Hi, Stavros.
Yeah,
Good to meet you. I'm Luis from the share team. I have a quick question. When it comes to the deploying in different areas, will WeatherXM, and this is an ongoing conversation that we have, but I would love to understand if there's any specific resources that we would be able to get as far as what is best for WeatherXM from a weather data standpoint when it comes to deploying? Like, say, for example, that we have 5 or 6 locations that could be optimal, but that are close to each other. Will we be able to know and understand where is best suited for you guys from a data standpoint and weather data standpoint?
Yeah, I think that I will try to address this question in the next slide. So,
Perfect.
yeah. Right. So here we have, of course, I will share this presentation with you at the end in order to have it, to have access to the link as well. I previously mentioned. So here is a simple. This is a very typical example that I use to explain the way that we should distribute our stations supporting the science of meteorology. So if I had just 4 stations to cover a large country, I would place one in the largest city, one in a coastal area, another in a rural low ground area, and the last one on the peak of the highest mountain of the country. In that way, covering these extremely different areas, I would be able to guess and estimate, let's say, the weather conditions in the areas between them, let's say. And here are the main mechanisms that affect the microclimate and the micrometeorology of the areas. First of all, let's have a look at this scheme. As we've already said, thunderstorms can be of a limited size, affecting areas of just a few square kilometers in an extensive flat area. It is quite common that showers can affect half of the cities, for example. I think that we've all experienced such a case. We all have experienced some experience of the micrometeorological conditions in the cities. So the concrete traps heat, and so the cities are much warmer than the surrounding areas. This is what we call urban heat island effect. However, the urban structures are so complex. I mean, there are buildings around, but also there are green areas. So temperature and wind may be significantly different within a few hundreds of meters. During the night, under clear skies and calm winds, temperature significantly drops over areas that are far from the sea and at the bottom of the valleys due to the phenomenon that we call temperature inversion. So the temperature can increase with height, and as a result, the surrounding hills of an area may have higher temperatures than the bottom of the valley. Sometimes this phenomenon is so intense that there are worth noting temperature difference between the first and the 10th floor, for example, of a building. And finally, sea breeze, which is caused due to the difference of the temperature between the sea and the land during a sunny day, and can affect the areas within the first tens of kilometers from the coastline. However, if a coastal city is present, then the intensity of the wind may decrease within a few kilometers instead of tens of kilometers due to the friction that the buildings actually cause. And in the next 2 slides, I want to give practical examples over real locations. This one is the city of Mumbai in India. With the triangles, I have spotted the locations that require, ideally, weather stations. And as you can see, this is a quite complex area. There is a large city. Okay, there is a large city, and the urban heat island effect is present, of course. Phenomenon that we previously mentioned. This means that we need a station within this dense area, urban area, measuring the phenomenon under which temperature is systematically higher than the surrounding non-urban areas. We also need another station to measure the systematic differences from the neighboring city in the suburban rural area. As we also said, the coastal front area may have a completely different microclimate than the inner parts of the city. This means that we usually observe more intense winds, lower temperature, and higher humidity in such areas. And we also need a station at the highest peak of the area, as the temperature there can be much different. Of course, as we said, valleys need extra stations because the flows of the winds are different, and also the temperature can be different especially during the nights. And inland rural areas can have large differences in diurnal temperature, which means that the temperature is really high during the day, during a sunny day, and maybe really low during a cloudless night. And this is another case of a quite complex topography. Let's say this is the Mount of Olympus in Greece, and you can see that the flows can be really different from the one in the different parts of this mountain. So the wind speed will decrease when it is forced to move aloft, but this leads to a result of the formation of clouds. So we have updrafts, then we have clouds, and we have more precipitation. So in case that we have the wind blowing towards this direction, we have more precipitation over these slopes of the mountain. But on the other side of the mountain, we have downdrafts that dissipate clouds, and so we do not have precipitation at all, or we have much less precipitation. Of course, the opposite can happen if we have westerlies, for example, instead of easterlies. So we have the wet areas of this mountain and the dry areas of this mountain. In this specific case, we also, as the air moves towards the lower ground areas, due to the gravity, the wind speed increases. Also, if we have airflows within valleys, along the valleys, then due to the tunnelization effect, we have much more intense wind speeds within the valleys. So as you can see, we need to capture different phenomena that are affected by the topography, by the land use. It's, as I said, as I initially stated, this is a quite complex problem that we try to solve. So summarizing, this is what I would suggest. So let's say that we have some hundreds of stations available to cover a country. Then what I would do would be to find the cities with a population larger than 1 million people and try to deploy 4 to 6 stations in average, of course, always over different areas of these cities. So dense areas, as I described, dense areas, lower dense areas of lower density. I mean, urban density, rural areas around higher areas, areas with significantly different elevation, urban parks, of course. But let's not spend too many weather stations in urban areas, because urban areas have already covered by other networks as well. Then it would be great if we had deployments over mountain peaks. I know that this is really difficult for many reasons. We need to have access to this area. Of course, when we maintain a station, we need to reach this area. So yeah, I totally understand that, but it would be great to have some stations over these areas, remote areas, that it's not very common to be covered by any stations. Of course, flat agricultural areas should be also covered, but here it will have a really extensive flat area with fields. I would suggest something like a minimum distance between stations of 60 to 100 kilometers. Then, as I said, deploy also stations in valleys, um, it, it, along coastal areas as well. Also, you can deploy stations at differently orientated slopes, as we explained in the last in our last case, and always try to find different land use areas. Like, I mean, cropland is different from forest, it's different from pastures, from dry lands. So let's try to cover all this diversity of land uses. Uh, and of course, try to make it quite how to say, a quite uniform distribution over the country. So that's it. That's all. I hope it was helpful. And if you have any questions, then just drop the questions.